Alright, so Unit 5 is all about experiments. So just remember the difference between an experimental study and an observational study is that an experiment will have a treatment. So basically the researchers are having the participants or the subjects do something, or they're giving them something. So they're changing something about their life. Alright, so let's take some rabbits. Let's say we had some rabbits, and basically a company is promising that they made the best food for these rabbits that make the fur soft and shiny. It increases their energy, and 100% of their daily vitamins and essential oils are inside of this food. It's wonderful, it's magnificent. So, in this case, they'll need to do an experiment in order to see if these things actually hold true. A lot of companies, they may report things, but unless they actually do a study, they can't say that it is actually fact, that these factors that they're claiming are actually true. So the experimental unit in this case are the rabbits. So an experimental unit is a single individual person, animal, plant. So it's basically one single item out of the items or things that they're experimenting on. So where they're experimenting on rabbits, an experimental unit would be a rabbit. And if you look at your vocabulary sheet, this is one of your words, and it's at the very top. So fill that in, experimental unit. In the case that the experimental units are actually human beings, then we call them subjects. So we no longer call them an experimental unit, they become subjects. And that's just the second vocabulary word on your paper, so make sure you fill that in. Now, the factor is just your explanatory variable that you're actually testing. So in this case, our factor would be rabbit food. And then the level is the specific factor that you're actually testing. So the level would be the hippity-hoppity rabbit food, or hippity-hop rabbit food. So there's only one factor in this case that we're testing, and then we're testing the specific hippity-hop rabbit food. So factor and level are also on your vocab sheet, so make sure you go ahead and put those down too. Alright, so remember, we already said treatment, but treatment is also on your vocab sheet. It's basically what the researchers are applying to the experimental units or the subjects if they're human. And then response, we've already talked about that before, but it's basically what you measure at the end. So if we were trying to do this research to determine whether or not this food does what it says it does, then in the end we would want to measure these three things to see basically how the fur is changed, if their energy is increased, and see, maybe test to see their vitamins, test their blood. Alright, so let's take this for an example. We're looking at whether or not the different types of fertilizers change the soil in, I'm trying to read and summarize at the same time, but basically we're trying to see which of the fertilizers work best on the different plots of land. So if we wanted to determine that, we basically are looking to see which one is going to yield the most crop when we're using these different soils, or these different type of fertilizers on the soils. So it tells us their methodology. So basically we have 15 similar plots. So we're making sure that they're similar because we don't want differences, and then that could be attributed for why the crops grew more food or less food. So they have to be similar. And we have these different plots of land. We're using the same type of seed. Notice we're making sure that that is the same as well, because we don't want that to be the reason why the crops grew better in one place than the other. And the only thing that we're trying to see or trying to make different is that the fertilizer is going to be different. That way everything else is what we call controlled, but we'll get there. Everything else is controlled because it's going to be the same overall, but the only difference will be the fertilizer. So at the end of the growing season, we measure whether or not the different fertilizers produce different amounts of food or yield, whatever these crops may be. Let's say they're corn or something. So first things first, since we're actually providing different fertilizers, we are doing an experimental study. So therefore, we can just kind of mark this as, I'm just going to circle, it is an experiment. Now, what are the experimental units? So when you're trying to determine what the experimental units are, basically you just want to look back at the problem and see what are they actually experimenting on. So in this case, if you look at it, they're putting fertilizer on 15 different plots of land. So the experimental units in this case are plots of land. Now the factors. Well, the factors are what are they actually doing? What are the treatments? So remember, your factors are basically your explanatory variable, and in this case there are fertilizers. They're different fertilizers. So notice I said different. Well, overall they're just fertilizers. So that's your factor that's being tested. And there are different levels of that fertilizer, or the factor. In this case, there are 3 different fertilizers. If we knew the brands, we would put the brands. But they are the 3 different fertilizers in this case, because we don't know the brands. Now, the response variable is, remember, what you're going to measure. So in the end, we're going to measure the yield of crop. So basically, how much of the plant or vegetable, whatever it is, grew. And here is asking how many treatments are there. Well, there's one factor, but there's 3 different fertilizers. So there's actually 3 different treatments in this case, because we are testing the factor at 3 different levels. Alright, so moving right along on example 2, let's say that we wanted to test different cake pans to see which one worked the best in the oven, so which one bakes evenly. So we are going to test an aluminum pan, a glass pan, and a plastic pan in the oven. Now the thing is, we don't want the type of oven to be what influences whether or not the cake bakes evenly. So we test those 3 different type of cake pans in the 2 different types of ovens. We'll test it in gas and we'll test it in electric. So the first thing is, to determine the experimental units, once again, you have to think, what are we actually doing these things to? What are we testing on? So you can pause it if you want to try to think, and then play to see if you're right. But the experimental units here would be the cake batter. That's actually what we're going to be testing these cake pans on, to see if the cake bakes evenly. So there are 2 different factors here, because there's 2 different things we're testing. Not only are we testing the type of pan, we're also testing the type of oven. So in this case, there are 2 factors. There's the type of pan, and there's also the type of oven. So for the levels, you actually have to consider each factor. So there are 3 different types of pans. So we're testing 3 pans, and there are 2 different types of ovens. So we have 3 levels of the type of pan and 2 levels of the type of oven. Now, response variable, remember, it's what you're measuring at the end. So in this case, we're actually measuring how evenly the cake is going to bake. So at the end of the experiment, the researchers can test how even the cake's baked. And for the number of treatments, you really got to think here, because we have 2 different type of ovens. So we have a gas oven and we have an electric oven, and we're testing each pan in those ovens. So we're testing the aluminum pan, we're testing the plastic pan, which is a joke, and we're testing what's the other one? Glass. So we're doing that in both aluminum, plastic, and glass. Just kind of oddly abbreviating just to shorthand. So if you look at it, the researchers are going to have to do 6 different treatments. The aluminum in the gas, the plastic in the gas, the glass in the gas, the aluminum in the electric, plastic in the electric, and glass in the electric. So that's 6 different treatments. So to get the number pretty easily, if you kind of see what's happening here, is you're just multiplying the levels together. So 3 times 2 is 6, because you have to do each pan and each oven, so you multiply. Alright, so let's take this example for instance. So let's say, unfortunately, which just actually happens with different products, but they find a product to be defective or faulty. So we have a brand of dog food, and this brand of dog food unfortunately was found to have contamination in it, and unfortunately some pets died. So it would be really, really hard for the brand of dog food to come back out and say, oh, our food is really safe now. Your dogs can eat it. We promise they won't die. Well, you can't really just make promises once those kind of tragic things happened. You actually have to do an experiment to demonstrate that your claim is actually true. If you remember at all, some years ago, Toyota came out with a Camry. I can't remember what year it was, but the Camry actually accelerated on its own. So unfortunately, this caused some deaths, and the Camrys dropped drastically in sales. So when they fixed the problem, they found it difficult to come back and just get their sales. So they had to do things like drop prices, have really good marketing plans, and etc. in order to actually get people to come back and buy their product because people were scared. So I would think pet owners would be pretty scared to buy this brand of dog food again. In this case, they would actually need to test their dog food on some dogs, or in this case it's dog and cats, but they would need some pet owners to participate in this experiment. But in this case, we have experimental units because they're testing the dog food on the dogs. It's not the pet owners that are getting experimented on, it's the dogs. So the experimental units would be given the dog food. And what are they testing in the end? They're testing their health in the end, whether or not their health is declined or if they died. But they couldn't just do it with just testing their dog food. They would also need a second group of dogs that are not receiving their dog food just to make sure there's not any other factors that are creating bad health. Because if they only did it in one group and gave them the food, then the brand may claim, well, what if it was this thing that happened that week that caused these dogs to die? It's not our food. So they would need a second set of dogs, a second group. That group is called a control group. And they'll need that control group to actually eat a different brand of food so they can compare the health at the end to see if this brand is actually getting the same amount of health factors as the other group, to where it's basically, okay, yeah, the brand's normal again. Or if the dogs are declining in their group, and that would be bad. They didn't fix their food. So in this case, the treatment would be the dog food. Ooh, that pink is not working out. Let's use blue. So the treatments are dog foods. Now, if you had you're testing the one dog food, but if you had two different groups, a control group like you should have, and you'll see that's a part of good experimental design, but then you would have two levels. But in this case, if you're just testing the one and you're actually experimenting poorly, then and just giving only one group the dog food that we think could or could not be contaminated, then that would just be one level. So it really just would depend on the researcher's design at that point to determine how many levels that factor had. Response variable, remember we are testing at the end to see the health. I don't know why I kept putting dogs, because it does say dogs and cats, so we'll just put pet food. So we are testing at the end pet health. So that's just an example of how this whole idea of factors and levels kind of work out. So here's our control group. Our control group, this is also on your vocabulary sheet. It's basically a group of people that we not necessarily set aside, but we have in order to compare the treatment group against. So we have a treatment group who's actually really receiving the real treatment, and then we have a control group that we're going to compare to see if the treatment was actually what caused some change in what we're looking for, what we're measuring in the end. Now, there can be confounding variables. So confounding variables are variables that could also influence the results. So let's say, for instance, we wanted to measure if a exercise program, maybe we have a group of people participating in P90X, and we want to see if they participate for just 3 weeks, if they actually do lose a certain amount of weight or something. So obviously we have a group of people participate in the program, and after 3 weeks we check their weight. Well, there can be other factors that influence their weight besides just the program. So those would be confounding variables that the researcher wants to control by making sure they have a comparative control group. So when I say comparative, people of the similar ages, similar weights, those are all confounding variables that could influence how much weight they lose in the end. So their original weight can be a confounding variable, their age can be a confounding variable, their eating habits can be a confounding variable. So what the researcher wants to do is they want to get people who are very similar in those things into these two different groups. A group where they participate in the program and a group where they don't. So that way they're controlling the confounding variables and just letting it be the program that is the main difference to see if that's what actually caused the change in the weight in the end. Alright, so there's a different, very similar example. I wasn't even reading the example. I guess I use the example a lot. At the bottom there's an example. So I kind of just talked through that example. Alright, there is a video in the actual PowerPoint I'm recording, so I can't really play the video inside of my recording because I'm not doing a screencast. So if you go on the website, you could watch this video. It kind of explains confounding variables a little bit. So if you wanted to do that, notice I said start at 57 seconds. That way you're kind of skipping past the other different things it talks about there. So if you want to watch that, it's inside the PowerPoint that's posted online. As I mentioned, the researcher wants to control those confounding variables, so they're thinking of what other factors could influence the result that they were trying to measure. So when they think of those, like age, original weight, what else did I say? Eating habits, they want to find people who are similar to put them in the two different groups. When they do that, that is what's called control. They are controlling for those confounding variables. Alright, so let's say, for instance, a professor at Cornell wants to see if his teaching style is what improves or doesn't improve his evaluations. At the end, when you're in college, at the very end, they ask you to do teacher evaluation, so basically kind of rate the teaching of the teacher. And he wanted to do this, so he went ahead and he did one teaching style in fall and one teaching style in spring. And what it is, what if one outperformed the other? So if you look at the bottom, let's say fall had a 2.93 rating, and in spring, they rated 4.05. So the thing is, since he did it in two different semesters, there could be a confounding variable of weather. So technically, he should do his design a little bit differently. It may be if he teaches the same class twice in fall, then he can teach them two different styles. That way weather, the confounding variable weather, isn't going to have an influence on how they felt at the moment. You know, a lot of times people feel more perky in spring, but I don't know. That's just a claim. I didn't do the research. So a lurking variable, this is another one on your vocab sheet. A lurking variable is basically a variable the researcher doesn't think about, and at the end you're like, dang, I should have controlled for that. So if it's kind of like something they didn't think about and it's kind of after the fact, then that's called a lurking variable. Once again, I can't play this link, but this link, and if you play it until 2:17, this is actually a pretty good example, and it's in the PowerPoint that's online. Just to kind of brief you on what the example is about. It's this kid, he's first time he's been on an airplane, and what he notices is every time the plane gets bumpy, the little red light above him turns on. So he makes this conclusion at the end on I think it's something like, why does the light turn on every time it's bumpy, or something like that. I can't remember what it is. But in the end, it isn't necessarily, you'll have to watch it, but in the end, it's like, it's not what really connects it. He has a misconception, basically, and which is a lurking variable because it's something he's not thinking about. So if you wanted to, you can go watch that, play it until 2:17. I can't remember the example clearly, I guess. Alright, so these are kind of like the differences. Notice in a confounding variable, it can influence the explanatory and it can influence the response, and we can't really tell in the end, if we leave this confounding variable in there, what actually produced the results. So we want to make sure as a researcher we think of those things and we control for them. If we think of them and we can't really control for them, like for instance, we can't really control someone's starting weight, we can try to get, like I said, groups that are very similar in weight, so we can kind of control for that. But what about if it was mental health? You know, what if someone's more stressed about eating weight? We wouldn't really know all these things, but as a researcher we can identify that when we write up our report and say, you know, there could have been these other factors. So you're still thinking about it, you're still identifying it. Now, lurking variable is kind of like at the end we're like, well, you know, we didn't think of this at all, and this could have also been the this could have been the reason for the change. So lurking one is more so like one you didn't consider, you didn't think about. Confounding is one that you did think about and you either controlled for it, or you thought about it and you realized you couldn't control for it, so you identified it. So basically the difference is lurking, the researcher didn't think about. Alright, so I'm not sure if you heard of placebo before, but a placebo is basically a dummy treatment, because oftentimes we as humans, if you're participating, or if you're a researcher doing an experiment on human subjects, we tend to think that we're getting healed, even though, just because we're given some type of treatment. So let's say, for instance, we have a headache and someone gives us medicine for a headache. Our mind can just think, oh, I'm taking medicine, I'm getting better. So in that case, researchers oftentimes have to use a dummy treatment just to see, well, is it really the thoughts that are thinking they're getting better, or is it really the medicine? So what they do is, let's say they're testing a new form of headache medicine. They give their actual pill that they're trying to test to one group, and they give the placebo pill, dummy pill, to the other group. It has no active ingredients. It's stamped exactly how the other one's stamped. Like, let's say, for instance, the real medicine had an M on it. Then the second one's going to have an M on it, but it has no active ingredients in it. That way both groups are getting that same mindset of, oh, I'm taking medicine. So then in the end, when they measure their ratings or their headaches, or maybe test their blood for whatever reason, they'll see is they both have the mindset. So let's see which one you maybe healed better. So that's the placebo. So the placebo effect is just the mindset of thinking, oh, well, I'm going to get better, I'm taking something, or I'm getting treatment. So the placebo effect, this is actually a pretty decent video. Once again, you have to go to the website and click on the link inside the PowerPoint to get to it. But it just shows how back in the day, people legit just thought they were getting better. So they would have these doctors come to them and just give them something. That way they thought they were getting better, and it necessarily wasn't something that was a real treatment. So they were giving people these things, and, in their mind they were getting better, and some of them actually really just got better. So here's my example where they're testing the new headache medicine. Let's say they had 40 patients that they randomly got, and they assigned them to different groups. So this is very, very important when you're creating a research model or research design. It's very important that you randomly assign your group of volunteers or your group of subjects. You randomly assign them to the groups. You don't want to just say, okay, well, these 20, you guys do this, and these 20, you do that. You want to make sure each of those 40 people have a chance of being selected in each group. So maybe you number them and you randomly pull the first 20 numbers, and those 20 numbers go in group 1, and the second set of 20 numbers go in group 2. So in group 1, let's say, for instance, they get the actual new pill that's on the market. Well, look what would happen if patients got no pill in group 2. They would just think, oh man, well, I'm not going to get better. So their whole mode, or their whole mindset would feel like, oh, well, I'm not getting better, so they may not get better as much as if they thought, okay, well, I'm actually taking a pill too, so I'm going to get better as well. So it's just a mindset thing. So the better design would be to make sure you had you're getting some type of treatment that in this case would look like a dummy treatment called a placebo. So we don't want them just taking nothing to where they're thinking, well, I know what group I'm in and I'm not going to get better. Alright, this video, this is actually a very good one. This would be the best one to watch, because this is actually a real surgery where people needed knee replacements. I don't know if you know anyone with a knee replacement, but it's basically where they go in and they replace the knee. So, which is a big surgery. So what they did is they actually had people in two groups, one that actually received the knee replacement and the other group that didn't. And what they found is that even the group that did not receive it, and when I say they didn't receive it, they got a placebo. They actually went through the entire surgery, had their knee cut open, had the doctor in there, they were put to sleep, the doctor opened it, the doctor didn't even know which group was and which group wasn't, or which patient was and wasn't going to get the treatment until he was actually in there cutting open, and then in the file it said don't. So he had to actually go through all the processes as if he was completing the surgery, so it'd basically take the same time length as if he really was. He played a video that, that way it kind of monitored his time, and that way the family that was sitting out in the waiting room didn't know whether or not they were the real patients getting the surgery, the real surgery, or if they were the patients getting the placebo surgery. So what they did, they stitched up both, sets of patients, let them go home. Patients still didn't know if they actually really had knee replacement or if they just had their knee sewn back up. And what they found is no matter what, the patient got better. So this whole placebo effect thing can kind of be real. I mean, these people were going in thinking they needed a knee replacement, which is a huge surgery, and you don't commit to that unless you're basically in aching pain, walking, or can't really walk. And my mom had her knee surgery, or knees replaced, so it's a very invasive surgery, and it takes a few months to heal. So, but in that video, you can see, if you actually go through and play it, this man is talking, and he's very emotional about finding out that he was actually in the group where he didn't get the real knee replacement, and he's just in awe about how much he actually healed without getting the knee replacement. So, okay, so let's just go ahead and talk about how to go about experiments. To experiment, you should have a design in your experiment. If you are just taking the experimental units you have and just giving them all the same treatment and then measuring the end, what are you really measuring? Just how they, from the beginning, how they started to the end? Well, what if they would have done that anyway? So a bad design looks like this, and this is, I'm sure, on your paper. You need to have a control group to compare it to, so the experimental units technically should be split and then compared in the end. But we're going to talk about that good design later. But that's how you experiment bad. To do an experiment, you should have 3 things present in your experiment. 1, you should have control, which I talked about a little bit earlier. You should control for all the different factors and making sure that the groups are as similar as possible, so that we can't say, oh, well, what about this? What about this? What about this? People are going to try to pick the research alive. I mean, we as humans should as well. We as non-researchers should pick it apart too. But most people, they just read the headline and they're like, oh, I take that as fact now. No, we should pick it apart to see if they actually did a good design, to where we should even take their information as a fact. So control is important. Randomization. Did they randomly assign these people into the 2 groups? That's very, very important. You can't just say, well, all the girls over here, all the boys over here, unless, of course, you're testing something on gender, but you can't say, hey, everybody who has short hair over here, long hair. It can't just be I feel like you 20 should be over here and you 20 should be over there. It should be random assignment. Replication is basically where, if it happened once and with one study, you should probably repeat the study and see if it'll happen again. So to generalize the information, you don't want to just complete it on, a group of people or a group of people in a certain area. You want to do it in different areas and different people, just so you can generalize your findings or your result. So replication is also very important. To repeat the study, make sure you get the same results. Okay, so here's how to experiment well. There should be random assignment, like I mentioned. That is very, very important. You should, in theory, random assignment equalizes all those other confounding variables. It equalizes the group. That way we can kind of start off at an equal slate, and then, if you assign randomly, basically you should get about the same type of people in each group. All right. So if you randomly assign, it kind of, in theory, equalizes the other variables that could influence the results. Okay, so here is where we talk about design. We want a completely randomized design, which that just basically means we randomly assign them into different groups where we have a control group. But there are different ways to have a completely randomized design. So a completely randomized design is like an overarching idea, and then there's different ways to do it. So here's the most general way to do it, or the most simple way to do it, is basically you have a completely randomized design where you randomize and compare your experimental units. So this is called a randomized comparative experiment, where you take your experimental units, you randomly assign them into 2 groups, and then you give group 1 a treatment and you give group 2 a treatment. Now, when I say treatment, it could be the new headache medicine, and treatment 2 be the placebo. So technically that wouldn't necessarily be a treatment, but it would be, in this case, a control group, if we use that example. because the control group, remember, is the group receiving either the placebo, which is a fake treatment, or no treatment at all. And then you just compare the results in the end. This is a good design, perfectly fine, nothing's wrong with it because it uses random assignment, it splits them, and it compares. So, once again, control, randomization, replication. You do need to know those 3 principles of experimental design. Those must be present in order to have a good experiment. Like I said, nobody's out there reading experiments online. They're just seeing the headline and being like, oh yeah, that's fact now. This, thing happens. But you gotta kind of look to see what they did. Otherwise, they're just doing research that is in their favor. Alright, so what can go wrong? Well, first of all, sometimes we don't want the subjects to know what group they're in, because if a subject or a person knew they were taking a placebo, then they're not gonna have the same mentality. So what we do as researchers, we do something called blinding. Blinding is actually a good type of it's something you can include in your design. And it's a good thing. It's not a bad thing. So blinding is basically just making it to where your subjects don't know which group they're in. So that's like giving them both the pill where each of them are stamped with the M and they're both the same color to where they both think they're taking the same thing. So blinding, and you can't tell them which group they're in, otherwise their mindset's going to change if they know one's a dummy pill or a placebo. So blinding is where the subjects do not know which group they're in. So that is on your vocab sheet. So once again, blinding is where the subjects do not know what group they're in. Now, in addition to blinding, you can have a double-blind experiment where neither the subjects nor the evaluator, the person at the end, know which treatment group they're in. So basically, kind of like if you watch the knee surgery one, the doctor didn't know. They really, really tried to make that double blind, but there is zero possibility he can actually pull that off. So they waited until the very last minute to let him know, even after they cut the knee open, that okay, you're not actually going to replace this knee. All right, so they really tried to make it double blind. But there are times where, for instance, like the headache medicine one, where you could make it double blind. So the doctor is the one that would know which medicine is given. But the evaluator, the person who's measuring, okay, well, how do you feel, at the end? Do you feel better? That person doesn't know which is which. So now when they give the reports, the researcher can go through and determine, okay, well, these set of people, okay, they were the ones with the dummy pill. They actually didn't do as well. They would know that. So the person administering the treatment and the person receiving the treatment do not know who's in what group. All right? So that's double blind. So the doctor doesn't know which little pills are in this cup that they're giving the treatment. The subjects. All right, randomized block design. Now, block design is a little different from this one because let's say, for instance, we identified something that we needed to control for. Well, we may need to split some people in groups before we give them the treatment. So randomized blocked design is basically where you split each group into blocks first. So, for instance, let's say we wanted to see the headache medicine again, but I got cut off there. But let's say for the medication example or the medicine, let's say, for instance, the researchers thought that age would influence the results. So first, they want to split their subjects into blocks by age. Maybe they have a group of 20 to 30, a group of 30 to 40. They want to go ahead and block off age groups. Or maybe they do, teenagers, and then they do middle age, or etc. So they can first block by age, and then in each block, they'll go ahead and give they'll split each block into a treatment and a placebo or a control group. So, let me see if I have that drawn out. No, I don't have it drawn out. So let me go ahead and give that as an example, because this is that example. Let me see. Nope. Let me go ahead and draw it out really quick. So let's say, for instance, we have 40 subjects to do our experiment with our medication, our headache medicine. And we think age would influence it. So we split it into 2 different age groups. Maybe we have over or under. Let's do under first. So under 30 and then over 30. So maybe we think the age would influence it. So after we blocked. So this is where we blocked. Now you can't randomly assign in blocks because blocks are by some characteristic. So when your block is by a characteristic. But then you split your blocks randomly. So you're going to use random assignment here. In each block, you're going to randomly assign which in this case, since we're splitting 40 subjects, there would be 20 here and 20 here. Or maybe we had, we only had 16 volunteers and under 30, and then the rest were in over 30. But either way, your number in each block then gets split randomly into 10 that receive the real treatment, and then 10 that receive the placebo, or basically these people would be your control group. So same thing that happens in the over 30 block. 10 will receive the treatment. Remember, you're randomly assigning who gets the treatment and which 10 get the placebo. Oops. Okay, I'm writing real sloppy, but that's because I'm writing on this. Alright, so then you'll go through and you'll compare inside of the blocks. You'll compare the treatment and control group in each block. You'll compare the results. So that's kind of what the design would look like. Basically, this shows that you're blocking first by some characteristic that the researcher is trying to control for. Basically, it's a confounding variable. So we think age will influence it, so we block by age. And then after we block, then we randomly assign those blocks into treatment and placebo groups, or treatment and control groups. Okay, so let's take our dog example that we've been working on. Let's say we're testing that food that they're claiming is no longer contaminated, but we think small dogs may, be a little bit different than big dogs in how they, digest the food or something of that such. So we get 32 dogs so these are experimental units to participate in our study, and we have 16 small dogs, so 16 poodles and 16 German Shepherd. So right there, what we're doing is we're first going to block by breed. So since we're blocking by breed, each breed is going to need to have its own treatment group where they receive the or they receive the potentially contaminated food, and then they'll receive a placebo or a control food, because we don't want to not feed them, because then obviously the health will deteriorate in the control group, so we'll just feed them some already approved food. Alright, so this is kind of what it would look like. We'd take our 32 dogs, we'd block by breed, so we'd have our 16 poodles or 16 German Shepherds, and in each block, because this is where we blocked, each block, remember this is blocking by breed, each block is going to get a treatment group and a control group, where they're eating the already determined safe food. So after you block, you split just as normal. So really, if you just look at, just the top of this is that other design. See if I can go back to it. That is that design, but this is where the block would be, and then you'd have your other block with the same exact pattern. So basically, you're doing that experiment, that design, but you're doing it twice. You're doing it for each block. All right, so that is a randomized blocked design where the researcher wants a block for a particular variable that they want to control. Alright, and so this whole idea of blocking for experiments is kind of like stratifying for sampling, where you basically have these groups in sampling. A matched pairs is the last design we're going to talk about. A matched pairs is basically where you want to first pair people up by some characteristic, and then give one of the people in the pair one thing, one treatment, and then the other person either the placebo or the dummy treatment. And then you compare each pair at the end. So for instance, if I wanted to see how no homework influences students' grades, maybe I would first pair up people by grade. Maybe I get the 2 kids with the highest grade, and then the next 2 kids with the next highest grades, and etc. Because I don't want to pair somebody who has a 98 with someone who has a 56, because maybe their homework habits are different. So first I want to pair, the student with the 98 with another student that has a 98. and then a student with a 56 with a student with a 56. And then out of those pairs, in the 98 pair, for instance, I give one of those students no homework for the rest of the semester, and the other one has to continue doing what they normally do. So they'd be the control group. So the treatment would be giving no homework. All right, so that would be an example of a matched pair design. So they're kind of like blocks of two, where we found grades to be, the reasons how we should block this. So you can kind of think of it like that. Or a person can be their own pair. So for instance, we give like a pre and post test after something. So I can if we're doing how does, eating no meat influence my health? Well, I can be my own pair because I can measure right now how my health is eating meat. I can measure that right now. So I would be my own control group because I'm measuring eating meat, what I normally do. And then maybe after some weeks of not eating meat, we measure my health again. So now I am my own pair. I'm being compared to myself in the control group, and then in the treatment group. The treatment would be not eating meat. So this is just explaining how before and after testing is also used, and it's also a matched pair design. So as I was explaining, a matched pair design is basically where you pair people up by a certain characteristic. Once again, it could be yourself, depending on the study. And then you have to, once you have the pair, you can't say, well, all people on the left, you go in treatment 1 or treatment A. That's not random assignment. Remember, you still have to have those 3 characteristics of a good experimental design, which are control, randomization, and replication. So you still need to have randomization. So you basically almost like flip a coin to determine which of those 2 people get to treatment A and treatment B. You can't just say everybody who's holding a pink card go in this one. That's not random assignment. All right. So another way is, you can, besides just flipping a coin, you have to flip it for each pair too. You can't just flip and say, okay, everybody with the T, I just flipped tails, you have to go in treatment A. That's not where each individual pair is getting a chance to go in each group. So you have to make sure it's fair for each pair. All right, so let me skim read this one. Oh, okay, so let's say that a researcher is testing 2 different methods to teach reading. Well, you'd still need a control group where a group wasn't receiving the reading methods. So in that case, not only would you have 2, you wouldn't just have 2 people, you would have to have a third child not receiving it. So it's kind of like you'd have, instead of a matched pairs, you'd have like 3 different, a triple pair, or something. No, that wouldn't be a pair anymore, a triplet, for instance. But you'd have to have the 2 treatments and someone not receiving the treatment. So this is all that this is saying. So if they wanted to test another method, they would have to find 3 compatible children to compare. And this one is where, let's say, for instance, a researcher wanted to study the effects of different skin creams for a certain skin disease. And if he had 80 subjects, he wants to divide them into 4 treatment groups of 20 subjects each. Well, he can use a randomized block design where the subjects are put into blocks according to how severe their condition is. Because what if a treatment is going to act differently in someone who just got the skin disease versus someone who's had it for a while and maybe tried several different types of treatments. So the researcher may want to first block based on severity, and then in each block give each of those 4 treatments. And then they would need a control group as well. So it would be a really big looking design, but we don't have to draw that one out. Your blocking, if you have to draw one out, would probably be just 2 blocks. I'm saying that for a reason. But anyways, the last thing I just wanted to mention is that statistically significant. What does that mean? Well, that means that your results as a researcher, the differences in the 2 groups were so large it couldn't have just been a coincidence. So you can't just have a little bit of growth. For instance, going back to the dog example, where you have a group of dogs taking the food that used to be contaminated, or the brand that used to have contamination in it, and a group of dogs who are already eating a food brand that is approved already. So if you have those 2 different groups, and in the end, out of like 20 dogs in each group, you have 4 pass away in the brand that's trying to get approved, and you have 2 pass away in the brand that is already approved. Well, it can be like, oh, well, see, it's their dog food must still be contaminated because they have more deaths than we do. Well, is that really enough? It's not like they had 18 deaths and then the other group had only 2. So statistically significant, which we'll talk about how to calculate whether something is in a different unit. But if something is reported to be statistically significant, then we know that the effects were so large that it couldn't have just been some coincidence. It was a bigger effect, a big enough effect to say, okay, yeah, this probably caused this to happen. And that is a vocab word on your thing, so I think that's the last one. All right, I know this was a lot of information, and this was another example, but I mean, it's kind of just showing you if some SAT prep class wanted to claim that they're the best in the world, they can make all these things happen, they can guarantee your money back. Well, they can't just say that. I mean, they'd have to show it. So they can't just take some kids and say, look, see this group of kids right here? We gave them the class and they improved by 18 points. Well, how do you know they just wouldn't have improved by 18 points because they already took it once and they kind of know now what the test looks like? So you'd have to compare it with a group who didn't have the course, and then compare their growth amongst the 2 groups and see if their growth was actually way more than the growth of the group who didn't go through the program. Alright, so that is it, but I know it's a lot of vocab. This is basically the unit, but it's a lot of vocab and it's a lot about experimental design. There's some other things we'll talk about, but at this point, I think you just need to watch some experiments, which there is a link. There's on the website, there's links to the experiments that you'll watch and you'll do the reports on. So that is on the website. So make sure you just start off by watching the first one and then answer the questions that go along with the analysis sheet that you guys should have. But yeah, I think it's just about watching some experiments now and kind of paying attention to some of these words, like did they blind, did they double blind, what were the treatments, what were the factors, what were the levels. So you got to kind of use the vocab to understand it. Alright, good luck. Adios.